All right. Hello, everyone, and welcome to Space Generation Advisory Council's webinar. Today's webinar is brought to you by the Space Safety and Sustainability Project Group. And today we have a very interesting topic that we have in front of you, whose title is SSA through Optical Sensors Observatory Development Using COTS Equipment. So all of you might be aware of the burning discussion that's happening all over the world regarding space junk or space debris. And for sure, in the years to come, it can lead to space traffic disasters. And really, in today's world, we don't have a good enough management system. So that's a topic on which we are going to learn about different ways and new techniques in which we can actually manage this problem and how we can be better prepared for tomorrow. And to do that, we have an expert with us, really the right person to guide you through and to tell you about all the latest technologies. Mahad Nair, who is an astrodynamist by profession and an ardent advocate of space sustainability. Mahad's areas of expertise are orbital mechanics, space mission analysis and design, spacecraft design, human spaceflight, and systems engineering. In particular, Mahad is pursuing the impactful role that emerging space economies or countries can play in the evolution of a global space traffic management system or best practices. Mahad is starting his graduate studies on the same topic at Purdue University starting fall 2023. After high school, Mahad was awarded the Department of State International Cadet Exchange Program scholarship, letting him to study and train in the U.S. Air Force Academy in Colorado Springs. His academic area of concentration was orbital mechanics and spacecraft design with the major field of astronautical engineering. Mahad is the recipient of several young professional awards and accolades, including the IAF Emerging Space Leader 2022 and AIAA Ascent Diverse Dozen 2022. In 2020, Mahad enrolled in a postgraduate master's program in space systems engineering and business engineering offered by Graz University of Technology in Austria. As the astrodynamics lead, Mahad led his cohort's SM80 design for a sub-geo CubeSat constellation capable of providing detection, tracking, characterization, and inspection services for geostationary and nearby anthropogenic space objects. His graduate research focused on sensor pre-processing, data acquisition, image post-processing, orbit determination, cataloging framework, and correlation of geostationary objects. Mahad is obviously an active member of the Space Safety and Sustainability Project Group and aims to contribute in projects related to space sustainability. So you can definitely understand the diverse background and expertise that our speaker has for today. And from this point forward, I would gladly pass on the stage or the podium to Mahad. Mahad, take it. It's all yours.
Subhrajit, thank you so much for the introduction, as well as all the administrative work that you have done to make this webinar a reality. I have around 10, 11 years of academic and work experience in the broader field of space sustainability. And I am looking forward to share my knowledge with all of you. Let's go ahead and start. The first slide is about my introduction that Subhrajit mentioned. I was very lucky to receive my diploma, undergraduate diploma by the American president, who back then was the vice president. And then I have a bachelor's in astronautical engineering from the US Air Force Academy in Colorado Springs, and then a master's in space systems engineering with focus on SSA. I have done, on the right, you can see me flying. So I've done a bit of flying as well. This is the picture at Edwards Air Force Base, California, doing some flight testing on T-38. Then the bottom left is me at Johnson Space Center, working on a simulator for one of my classes during my undergraduate, in which we designed a Mars mission. And then on the right is me with my glider. I'm a certified instructor pilot in gliders as well. You can see my name here. So been very fortunate to get a lot of opportunities and it's time that I start giving it back as well. So let's go ahead and start this webinar. Um, so the sequence of my presentation, first of all, we'll talk about the terms SSA, SDA, STM, a lot of jargon being thrown around pertinent to space sustainability. Then we'll talk about space domain information fusion model and what makes SSA challenging. Then a little bit of literature on optical sensors, and then the main part of our webinar, which is the SSA observatory development process using commercially off-the-shelf equipment, such as telescopes, mounts, detectors, and so on and so forth. So moving forward, this is a heavy slide, but let's talk about it. Basically, initially there was only one term, which was SSA. Why? Because space was big enough and there were not a lot of actors or stakeholders who business. So 20 years ago, or maybe 15 years ago, the only term that was being used was space situational awareness, and it's primarily refers to keeping track of objects in orbit and predicting where they will be at any given time. Now, SSA is operator specific, and it is focused on the owner operators of space objects and their responsibility to assure the safety of their own object and their own business. But what happened was, after there were way too many owner operators and the commercial space started booming with satellite constellations going into space, and the number of objects started increasing in an exponential manner, what happened was there was a new definition coming from the US Air Force or the US Department of Defense, and that was space domain awareness. So now we are moving from individual responsibility to domain responsibility. And the domain is including detection. It's just in SSA, it was mostly just, where the objects are, orbit determination. But now one of the biggest topics in domain awareness is characterization, the identification of objects. What is their role? What is their behavior? So SDA is about the complete space environment that we are using, and is about all objects. It is about rocket bodies. It is about everything else, dysfunctional satellites, debris, everything that is there in space. So now we want to create a domain awareness. And then the next term, which is also used, is space traffic management. So space traffic management is primarily a commercial term, and it is analogous to air traffic control for air domain, in purely commercial, and it is something that is evolving right now. And there is even a question whether space traffic management or a global space traffic management system is the right way to move forward. Or maybe we just have to establish best practices and move forward from there, because the dynamicity of the space environment makes it very difficult to basically have a global system. So that's why there is a lot of discussion about polycentricity or having distributed method of ensuring space traffic management as well. And there are some principles of regulating space traffic management, which is you have to define the terms. For example, probability of collision. Now, owner operators have different definitions of the probability of collision or the threshold, after which they will apply their maneuver to stay away from a collision. And then establishing minimum standards of conduct, assigning liability, which is a huge discussion in space policy and legal domains, because the Outer Space Treaty is a guideline and for the most part does not assign liability to different space actors or stakeholders who can, out of their will, just pollute space as well. And you have to distinguish between the orbits and how different orbits behave. Geostationary or geosynchronous orbit definitely behaves very differently as compared to the low Earth orbit environment, and so on and so forth. And then allocate responsibilities and authorities. So these are some of the literature, some of the discussion that space traffic management is going through. Now, this is a really funny diagram. These three terms, SDA, STM, and SSA, they are not mutually exclusive. They have elements there that are overlapping, but here you can see this diagram I have taken from my graduate studies. And you can see here that the SSA is not only about man-made objects, it is also about space weather and near Earth objects, which includes natural objects as well. In man-made objects, you can see that there is detection, the first step, tracking, which is continuous detection, characterization, identification, cataloging, and predicting the behavior. And it is very, operator specific. But then you go here to space traffic management, and then it is accountability, licensing, technical constraints, consensus, agreement, rules, regulations, insurance, all of these things come into the governance part. And then the domain part is attribution. Who should we attribute it to? The threat and risk assessment, intelligence, and then you can see that all SDA, SSA, and STM are also constantly interacting with each other as well. So don't get confused by it, but just have a little bit of distinction in your mind about what these three terms are all about. Then once again, this diagram is about stakeholder relationships with SSA, SDA, and STM. And primarily, you can see that all sorts of stakeholders have their stakes in all of these. So for example, commercial SSA data or service providers provide data to SSA and SDM. And then SSA and SDM also, provides data to military spacecraft operators. So you can see that it's really complex. It's a mesh of a lot of relationships between a lot of stakeholders, and all of them have to play a positive role to make sure we keep space sustainable. Now, this is the space domain information fusion model. And if you are interested about space sustainability, you must know Dr. Moriba Jah from University of Texas, Austin. He's also the chief engineer for this company called Privateer that aims to provide space domain awareness services. So here we have different levels. So level 0 is where the data and information originate. And then we have level 1, which is the heart of foundational information. And level 2 is like the hard work, make or break, whether you have to perform the maneuver or not. Level 3 is develop the space domain awareness picture. That's where we discuss about all the thousands of objects that, concern us. And then the level 4 is potential courses of action and decision making. So you can see level 0 here, level 1, level 2. So what I want to point out here is that when it comes to optical sensors, and when it comes to, just using one telescope to basically looking at objects, it's just very small part of the complete domain awareness. Basically, it is information exploitation and fusion and inference on space objects, event detection, event tracking, event identification, characterization. So basically, even after all this presentation and all the work that gets into the development or establishment of an astronomical observatory that can be used for SSA, you are still basically just one cog in the grand machine of space domain awareness information fusion model. So just to give you an idea about how big the space domain is and the different levels of data that there are. So what makes SSA challenging? SSA can be challenging in a lot of ways. The sensors, radio frequency, interference, flyby and mitigation, orbit determination, propagation, which is one of the huge topics, because orbit determination from optical sensors is quite difficult as opposed to orbit determination from radar sensors. It is because in optical sensors, you need to have 3 measurements from 3 different sensors and triangulate your way to determine the state vector, and then use statistical orbit determination methods to come up with the propagated state matrix, and that leads to the covariance matrix, which tells you how uncertain your position is. So basically, a lot of challenges are there in SSA. So now, real quick, we will go over some literature on optical sensors. So basically, optical sensors are not new. The first optical system observing space objects was, of course, our human eye. And the space race was, picking up pace. Even they had people sit in remote areas with really clear skies to actually look at the Russian satellites and determine their right ascension and declination angles so that they can determine their orbit. And even in the 1950s, US started a network which is called Baker-Nunn Telescope and Camera. So this is the telescope that you can see. It's the 1956-57, and it had a 0.5 meter aperture. So it was half a meter wide with 30 into 5 degrees field of view. So you could see the space objects because it was really important. Once you're putting objects in space, you gotta know where they are. And this is the first space object that was tracked by Baker-Nunn. And as you can see, it's a black and white image with just pixel detection of, and this is, we're talking about 1950s. So the technology is like really, really old, analog, and, but still, even at that time, they were working on making an optical network that provides them space situational awareness. This is the complete network of Baker-Nunn telescope sites that is from 1958. And you can see that they have them in the majority of the countries. And the one in Spain was refurbished in 2007. And basically they spent 500,000 euros to replace the equipment and have new equipment come in. And that is used by IZON, which is International Scientific Optical Network. And IZON is Russia's academic network. It comes under Kalish Institute of Mathematics, Russian Academy of Sciences. And they have these telescopes spread across primarily in the Northern Hemisphere. And it also serves to contribute towards space domain awareness, space traffic management. And it's purely a commercial and academic network. Now coming into, the space surveillance and the EM spectrum, primarily we are using sun as an energy source, and our wavelengths here are primarily the optical wavelengths. This is our sweet spot if we look at the irradiance and the wavelength graph, and we basically are relying on sun exciting our sensors and using passive sun energy to have the image of the object that we're looking at. And the good and the bad. Okay, so about optical sensors, they are low cost as compared to radars. They use less energy because we are dependent on passive energy from the sun. They have long range. For example, geostationary orbit is best observed by telescopes as opposed to radars. And you can see here in the radar equation, we have radius to the power 4th as opposed to the equation for optical systems in which we have radius to the power square, and it's in the bottom, in the denominator, in the inverse term. So we can see that through optical systems, we can actually look far, and it has high surveillance rate. Now, the bad is it's obviously weather dependent. Usually it's only nighttime operations. Now we have some companies like Numerica or Slingshot Aerospace that are going into daytime tracking using different sensors and filters. And then we don't have any range information, which is basically the biggest challenge. It only gives you angles, only information, but the angles that are given by optical measurements are actually better than the angles that you get by radar measurements. But in radars, you have the range and range rate. So you have range, azimuth, elevation, and the rate of change of range, azimuth, and elevation. And basically you can put all of that in a state matrix and put that into through numerical integration and statistical orbit determination to yield the covariance matrix. The method to do the same for using telescopes is quite difficult. In the optical system applications, we have two primary applications. We have non-resolved detection. Basically, you just see a pixel, and then resolved imaging. So for resolved imaging, you need really powerful telescopes with really big apertures and really good signal to noise ratio. And then you can actually see the shapes maybe of the solar panels of other objects, and that's the resolved imagery. But even with non-resolved imagery, you can use astrometric measurements. So basically, astrometry is the process in which you compare the position of an object with the starry background, and you have a database of stars, and the database has all the angles of where the stars are. So basically, when you take images of space objects, you look at the object and then you compare it with the background stars and you find your angles. And that is called the process of astrometry. And then radiometry tells you about how bright the object is. And even using the brightness of the object, you can basically simulate the brightness in a computational software on Earth, and basically plot a graph of how the brightness is changing. And that can tell you information about how the satellite is tumbling or rotating or things like that. I'm seeing that there is, okay. Yeah, so you can put your questions in chat, and Subhajit, whenever there is a question, please feel free to interrupt me and speak it out loud, as I'm unable to see the questions while I'm presenting. So moving forward, when we talk about sensor architecture, it means a group of sensors that are dispersed at geographically diverse locations to make a complete network. And the real thing to understand here is there is no space situational awareness possible without a network of sensors or a sensor architecture. You need to have sensors dispersed all over the globe to take consecutive measurements of objects going into a decentralized system, which is comparing measurements from the neighboring sensors to basically do the orbit determination and yielding the uncertainty. So here we have some comparison about optical systems for ground-based, space-based in LEO, space-based in GEO, and then ground-based laser ranging. But basically, advantages are for ground-based, it's subject to weather. In LEO, it's a higher cost and sensitivity challenge, plus it's very difficult to come up with a scanning pattern in the low Earth orbit. Then in the geostationary Earth orbit is actually optical systems can work in a phenomenal manner in geostationary orbit. For my master's thesis, we designed a sub-geo constellation of small satellites, and we just put a small telescope under the geo ring. And since we were under the geo ring, we were traveling faster than the geo ring, and we were looking outwards at the geo ring. So by having maybe 15 to 20 sub-geo birds in an orbit that is under the geostationary orbit, you can basically have a complete situational awareness of your geostationary orbit, which is really, really important because the satellites that you have in the geostationary orbit are actually exponentially expensive as compared to the satellites that you have in low Earth orbit. So when it comes to the insurance of space objects, they actually want services for the geostationary orbit first because it involves a lot of cost. Okay, going ahead. It's a simple how we gather signals. So we have the sun. Sun is, putting its light on solar illumination on the object. And we have the sensor here, which is looking at the object, and that those photons are basically coming from the object and coming into the sensor, and then we take the picture. Basically, one of the biggest issues is we have to focus the object on the detector. So if this is your telescope and the light is coming, you have to focus the light on your detector, and it also determines how big your field of view is going to be and how big your focal length is. Since we have a diverse audience for this webinar, I'm not going into the specifics of optics, but primarily the things that you have to remember here is the bigger the aperture of your telescope, the bigger resolving power it is. And the larger your focal length is, more magnification you have. The smaller your focal length is, the faster your telescope resolving power is. This is the equation. Basically, don't worry about it, but just get the gist of what it is, what we're talking here. So we have the signal power reaching from the object to the sensor, and then these are all the things that are playing a role in its signal noise ratio. Okay, my apologies. I mentioned that the d square factor is in the denominator. That was a slip of tongue. It's in numerator and it's directly proportional to your signal strength. So then we have the things that are playing a role in your space object signal equation is the satellite irradiance. So how much bright the object is, how much power it is generating on your pixel on your detector. Then you have the attenuation by the atmosphere. You have the telescope aperture diameter, and then you have the telescope obstruction and transmittance and reflectance losses. Okay. Okay. I'm going to apologize once again. I just confused the terms. The D here is the aperture of your telescope diameter. So the bigger the aperture, the bigger your signal strength is. The other D, which is the distance between the object and the sensor, that's in another equation which I did not add in this presentation. So don't worry about that, but just focus on all the things that are mentioned here in this equation. Okay, that was the not fun part of the presentation because it was math, a lot of literature, optics, so on and so forth. But now is the fun part because I have added a lot of pictures and I will walk you through the process of how to build your own SSA observatory and how you can start conducting or taking measurements for contribution towards space traffic management. So first of all, whenever you are talking about building an observatory, you have to select a site. And if you think about some of the biggest telescopes in the world, they are at sites which have really dark skies. So deserts in Chile have a lot of European Space Observatory and other telescopes. Similarly, some mountains areas in Colorado or other areas, they have observatories. They have some in Tenerife, Spain, Alaska, Diego Garcia, a lot of places basically. So point is you need to have clear, unobstructed skies. You need to have an elevation map. The higher, the better, because there's going to be less atmospheric attenuation and less elevation hindrance. Clear night skies, less light pollution, the less, the better. So you have to be in suburbs. It's not really possible to put a telescope right in the middle of New York City. That's why you don't have one. Otherwise, you will, the observatories that you primarily see are functional ones are in remote areas. The observatories like the one in London, the Greenwich Observatory, or the one in Los Angeles, they are now mostly museums and they are doing outreach purposes instead of actual taking data. But nonetheless, even if you have a telescope in a city, you can still do some research with it. So moving forward, let's talk about Bortle scale. A Bortle scale measures the quality of the night sky for a particular location. So here you have 9 different scales. So if the Bortle scale is 1, it means you have excellent dark sky sight. And if the Bortle scale is 8 or 9, it means you are in the inner city with lots of billboards and lots of light pollution. So this is really important here because at the end I will discuss observatory rating scale, and basically this determines the complete quality of the data you are going to procure from your observatory. So if your observatory is in clear skies, my personal experience is as long as the Bortle is 5 or 6, you can still do some SSA with it, not for the smallest objects, but for some objects, you can definitely do some SSA and orbit determination. But if you are in 7, 8, or 9, it's going to be a bit difficult. Then you have the light pollution map. So coming from the Bortle scale, you can go to this website and basically look at the light pollution area. So whenever you're doing a geographical survey to choose a location for your observatory, you have to refer to the light pollution map and see which areas have least light pollution, and then pick the area according to that. Then we which is called Clear Outside. And Clear Outside is open source graphical data repository, and it takes inputs data from a lot of resources like NOAA, UK Met Office, Norwegian Met Office, and it puts them together. So for example, for D1 in United Kingdom, it tells you the astronomical conditions. So if you want to do a more detailed survey of the location or couple of locations that you have chosen, it tells you red means that there is no observation is possible. And it is primarily because the percentage of cloud cover. So total clouds, low clouds, medium clouds, high clouds, and you can see that the cloud cover has totally stopped us from doing an observation on this particular day and time. It also tells you the class. It also tells you the quality of sky. So you can also just put a location in and access this resource, and this will tell you about the quality of your skies. Another thing that you can do is you can buy a sky quality monitor. So this is a sky quality monitor, and it basically measures the sky's brightness in magnitudes per square arc seconds. And if an observatory developer wants to quantitatively verify the atmospheric conditions, then you can just put this at a location where you plan to build your observatory, and you start collecting the data. So these things, making an observatory takes time. You have to get the fund, the budget, the approvals. So it's good to start ahead and just start doing your geographical survey and start gathering the data to basically maybe have a data of 3 months or 6 months, preferably ideally 1 year. And it will tell you, you can do a comparative analysis of the different locations that you have chosen for your observatory. But here's another thing. It's called a multi-criteria decision analysis. So this is a really comprehensive decision matrix, and the criteria here is photometric night fraction, which basically tells you about the cloud cover and night sky brightness, sky transparency, your altitude, your terrain slope, your seismic vulnerability. You don't want to build an observatory at a place where you get a lot of earthquakes. Then you have your wind speed, because obviously wind speed is going to affect your night observation. And then accessibility. Obviously, you need to have, the road access, and then the land use or land cover. So I will, this table is from a really nice paper, which is optimal site selection for an optical astronomical observatory in Pakistan using multi-criteria decision analysis. And basically, all the different criteria that is there, you can use open source data that is available to basically extract the maps for your particular location, and then put the quantitative numbers in your decision matrix and choose a final location. For example, if you have 4 prospective locations, you can pull out all the criteria for all these locations and put them in a decision matrix. So the map right here, we have photometric night fraction. Then you can see the legend here. Not going to go into the details here, but it basically tells you how much cloud cover there is. Then we have the night sky brightness. Then we have sky transparency and aerosol concentration. Then we also have altitude. Apart from that, we have the terrain slope and gradient, how that helps you or not helps you with your particular location for the observatory. You also have the seismic vulnerability. So obviously you gotta see where you have land which is more vulnerable to earthquakes and seismic activity. You have wind speed, accessibility, and land use. So the crux of the matter is site selection is important. And now you have all these factors or parameters that you can actually use to come and decide on the site that you want to use. Once you have your site, one of the foundational thing that you're going to use is mount. So a mount is basically a device that holds your telescope and helps its movement across the night sky or the cosmic sky. And there are different types of mounts. One is alt-azimuth, which is also called altitude or azimuth mount. An altitude azimuth mount does not need to be to be calibrated with the North Star. You can basically put it anywhere in any direction, and it is going to basically calibrate itself with the sky map and start operating. Um, on the other hand, we have equatorial mounts, and equatorial mount is a one in which you point out one axis of the mount with a northern star. So once you have pointed out your one direction of North Star or the Polaris, you basically have eliminated one axis. So if you have two mounts of similar capabilities, the equatorial one is going to have more accuracy because it has eliminated one axis and now it has to just move in two axes as opposed to an LTAS mount, which primarily looks all over. However, there is the mount which is called equatorial fork mount. In a fork mount, I'll show you the picture in the next slide. But basically, it's a fork, and you put your telescope in the fork, and the fork moves all across. In the normal standard mount, what happens is you get the meridian flip. And the meridian flip is when you have to flip from one side of the meridian to the other side, you have a chances to basically hurt your equipment because its counterweights are going to hit the tripod. So what it does is it basically goes parallel to the ground. It completely changes its position and then it goes to the other side of the sky. This limitation is not in the fork mounts because in the fork mount, basically you see that it can basically goes all over from horizon to horizon. And that's the reason that it gets rid of the meridian flip. And now you don't have a time interval where you miss the data collection. But fork mounts are very advanced. This one is from Software Bisque, which is a company in Colorado. And these two mounts are from PlaneWave, which is an amazing company that produces exceptional quality mounts. And these mounts are usually, they have their direct drive mounts. They don't have any backlash from the motor, or if there is very less. Their slew speed is amazing. As you can see, this mount is rotating. So basically, the slewing speed of the mount is going to determine if you can move your telescope with the same speed the object is moving in the night sky. So you have to be careful in selecting a mount with sufficient slew speed that can cover a wide range of orbits. Then whenever you select a mount, every mount has a weight limit that it can carry a telescope of 50 kilograms or 100 kilograms. So you have to keep that in mind. You have to keep the power requirement in mind, how much power it takes, and whatever your location is, if you have that kind of power available. Then all of these are go-to mounts. A go-to mount is basically a mount which is automatic. Basically, you can just use software to calibrate the mount, and it basically knows where the night sky is. So you don't even have to do anything yourself. You use a software, primarily Stellarium or SkyX, and you put in your input and the mount will do its job. This presentation does not cover the software segment, but we'll go to the software segment in another webinar, since this is supposed to be a series of 3 webinars. So the second and third one will be a ground segment, and one will be about software. Then the sidereal tracking means that it can track the stars as the stars are moving. So then you get the background that you get is a crisp star background. Then you can compare it with the star database and do your astrometric operations to find astrometric calculations to find the right ascension and declination axis. Then on the other hand, it can also track ASOs. So the latest mounts can take input in the form of 2-line elements, and they can just track the object and not track the cosmic sky. So these are the 2 different modes of operation, but this is more pertinent to the software segment, so we'll talk it later. And they have on-axis encoders, which makes their motion really smooth, and then they don't have the meridian flip as well. So these are some beautiful, beautiful mounts. I personally have used a couple of them, and they're amazing. Now, after the mount, which is your foundation, you have the optical tube assembly, or in other words, telescope. So usually for the first telescope is called the Newtonian telescope. It's also called the reflector. You look from this is your eyepiece, and there is a mirror here. So light comes in, reflects from the mirror, and then you see it from here. Then you have a refractor in which your eyepiece is right in front of the opposite side of where the light rays are coming from. And that's a simple reflector and refractor telescope. But the real fun is when you combine reflection and refraction, and that's called a Schmidt-Cassegrain design. Excuse me. So a Schmidt-Cassegrain Cassegrain design is also called a catadioptric configuration that you can see here. And basically the light is coming from the light source. It is reflecting off your primary mirror from the periphery. It is going into the secondary mirror, coming back here, and then you have the focus here, but you use a set of lenses to get rid of different optical aberrations. And then here's your eye or your CCD or detector. And the astronomical community or companies are making rapid advancements. So in Schmidt-Cassegrain design, you have Ritchie-Sheraton telescope, you have Ultra CRC, you have Richard Dahl Kirkham, and then you have Ryla and Ryfast. And the two big companies that are producing these ones are once again Planewave and Officina Slayer and Takahashi. Takahashi is a Japanese company. Officina Slayer is an Italian company, and Planewave is an American company. And basically, all of these designs have different combination of mirrors and lenses to basically get rid of the small errors that are left in the end inherent to optics. And for example, in Ritchie-Sheraton, they use hyperbolic primary mirror and a hyperbolic secondary mirror to eliminate off-axis optical errors. And then in Ultra CRC, they use a two-lens collector group near the focal plane and the hyperbolic secondary mirror, and so on and so forth. So you don't have to worry about fully understanding the arrangement of these different mirrors and lenses. But what you need to understand is that the Schmidt-Cassegrain design is constantly being optimized by the companies to make sure we have less and less optical aberrations. And look at these beautiful telescopes. So here you see the old one telescopes, but these are optical tube assemblies. And this is, all of them are catadioptric or Schmidt-Cassegrains, but they have this one. For example, this one is a Ryla and a Ryfast telescope. This one is CDK from Planewave. And even a fun thing is you can basically have an array of telescopes in one mount. So you can use one optical tube assembly in one mount, or you can use 4 or even 16 in one mount and have fun with it. So these are some really beautiful looking telescopes. And for example, a 0.5 meter telescope can cost you around $30,000, which for personal use is expensive. But if you fundraise for it through your organization and make a nice proposal, then your organization or institution can fund it. And a lot of these telescopes are there in a lot of American universities, observatories as well. We have one like this in Arizona State Observatory, Purdue Observatory, MIT's observatory. So a lot of fun. Now the fun part is detectors. So a detector is basically sort of like the eyes of your system. And once you have the telescope, which has done its magic in bringing all the photons to a focus, you have your adapter, you have your camera basically. So it can either be a CCD, which is charge coupled device, or a CMOS. And previously, a CCDs had more sensitivity, but these days, even the CMOS, which is complementary metal oxide semiconductors, which really made an impact when DSLR cameras came out. There are also now the amazing CMOS chips are coming that you can use. SBIG is one of the companies that produces some of the best CCDs. But while you're purchasing your CCD, you have to obviously consider your budget. But some of the things that you can read about later while making the decision or is the sensitivity, the quantum efficiency, the readout noise, the temperature, and the stability. So you can look out their metrics and compare them with other cameras and see which camera is more suited for your needs. Okay, so in essentially you just need three things. You need a telescope. This is your telescope. This is your CCD, and it is on a mount. But now we're going to talk about integration, that how you're going to integrate this equipment. So here you can see that you have a lot of things that are coming in between this imaging crane. But first of all, we are going to talk about back focus. So back focus means that this optical tube assembly that you have purchased does not focus right at its end. It basically focuses after some distance, and this is the focal plane. So what you do is you have to put your CCD or your camera at this focal plane, and this has to be exact. Why? Because then you won't be able to focus. So for example, if this telescope's back focus is at the distance of 300 millimeters from its back end, you gotta put your camera at 300 millimeters. If you put it at 310 millimeters, you will be out of focus. And usually, like it's not possible to move your primary and secondary mirror unless you have motor focusers that you attach with your primary mirror and secondary mirror, and then you can do minor adjustments there. But it is important to keep your detector as close to focal plane as possible. And it also, and for that, you would need an adapter. So you would have to go to a local manufacturing shop, design it. Usually your equipment manufacturer can tell you now the exact back focus, and then you will just go to a machine shop and get it manufactured. Like in this optical crane, this is the camera CCD, and these are the things that I will discuss in just a bit. And then this is covering the distance, but this in the middle is the adapter here. The second thing in integration is counterweights. So your system is not always balanced. For example, when your telescope is, rotating and, covering the night sky, it goes to all directions. And when it goes to all directions, you get different moment arm and moment of inertia, and that puts different amount of weight on motors. So in a typical configuration, you add counterweights to in your configuration so that even at maximum left or right positions, your telescope is balanced. And in this manner, you don't put a lot of weight on your motors and you will not burn them. So these are equatorial or classical mounts, but even here you see these are the counterweights that they have put in to basically balance this on the rails. And here they have, this is the counterweight, these are the counterweights here, these are the counterweights here. So you always have to add counterweights to impart minimum sort of weight on your equipment. Then integration, you have balancing, because you, apart from counterweights, you can't put your telescope way ahead or way back. For example, in this configuration, this is a fork mount, and the fork base can actually, when this telescope is rotating this side, the fork base can be a hurdle for the bottom side of the telescope. So you have to balance it, and for balancing, you use dovetails, and these are the dovetails. And in these dovetails, or basically rails, you can put your telescope ahead or back. Similarly, there's a dovetail. This is a dovetail. You can move your telescope ahead or back. So apart from counterweights and back focus, you have to base your system as well. For example, a very practical problem that you can encounter is that if your CCD and is 300 or 400 millimeters behind the backside of your optical tube assembly, and you have to rotate it, or if it has to observe an object here in the night sky, it will rotate, go to this side. But if your CCD hits the fork base, then you have to move it ahead. Now you move it ahead, and your motors start buzzing, ting, 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 and they'll say that you're putting too much weight now. So then you get counterweights made, and it's basically an iterative process. You have to do it again and again and again to find the sweet spot, have complete freedom of movement of your telescope. It is focused and it is balanced. Another thing that you see in that diagram or right here is called a filter wheel. And a filter wheel is a device that you use for adding different filters. And basically, the night sky is not always in ideal conditions, or sometimes you just need data for a specific wavelength. Maybe you need data from red or green or blue, maybe infrared. So what you do is you put these filters at specific slots, and you can see that these slots have numbers on them. And then if you have to program that number 5 slot is the blue filter. So in your software in SkyX, you'll put the blue filter at number 5th slot, and then it will, whenever you have to go to that side, you'll just press 5, and this will rotate automatically through a motor. You can see that this is connected with the power and with the LAN as well. So this you can just use your computer to change the position of the filters and get different data from different wavelengths. And basically in deep space astronomy, you get data of different wavelengths and then you add them together. So usually LRGB, different wavelengths, you get the data of all those wavelengths and you stack them together, and that's how you see the colors. Because I mean, if you are looking at the pillars of Creation or Orion Nebula or Andromeda Galaxy, you're not going to see the colors right off the bat. You have to take pictures or frames from different filters and then stack them together to find a colored image. These are different sets of filters. You can see the wavelengths here. You don't have to memorize them. You can just Google them whenever you need, but some special ones are hydrogen alpha filter, which you use to look at the sun. And then you have S2 and O3 filters. Then you also have a light pollution suppression filter. And what you have to make sure is that your filter size, if it has a boundary on its side, it's called a mounted filter. If it doesn't have a boundary, it's unmounted. You have to put unmounted filters in your filter wheel, and then your filter wheel is attached here. Or if you can see, your filter wheel is attached here. This is your filter wheel. So your camera is basically looking through the filter wheel, or the light that is coming through the filters to your detector chip. Okay, so now this is the optical imaging or imaging train. So once you have integrated all your equipment, you have your CCD, you have your filter wheel, you have your detectors, you have your adapters that is connecting. But here you can see that there are a lot of things as well. You have a guider scope, you have an auto guider, you have a finder scope, you have a rotating focuser, you have a lot of auxiliary equipment. So before I go into the auxiliary equipment, I want you to understand that whenever you're building an observatory, you really have to look at the imaging plane and see where the fault can be. If you're not getting a perfect image, maybe your collimation is out of line. Collimation means that you are actually looking where you're trying to look. Because when these big telescopes are transported from the manufacturer to your place, sometimes their mirrors get moved around, or there is a little minor adjustment is needed. So you have to understand your optical train or imaging train and see where the fault can be. And then basically you can remove the things from the optical train to see if individual items are working together. For example, if you are seeing a spot on your image and that spot is there in all the images, there is a dust particle. It can be either on your CCD sensor, on your filter, or maybe on your primary mirror or secondary mirror. So then you have to do your fault isolation and clean your equipment. But here are some of the auxiliary terms. Usually we use, like here you have a smaller telescope with a bigger telescope. So when small telescopes are mounted parallel, they fulfill two purposes. And it can either be used as a guider scope or as a finder scope. And the guide scope is basically for auto guiding, and process uses a small secondary camera And basically your computer can take inputs from two cameras at one time. SkyX can take two inputs, or Stellarium as well, and it helps improve the tracking accuracy of your equipment. And then similarly, a finder scope is a scope which has a bigger field of view. So you can find the object in finder scope and then have your main scope focus on it for more resolved imaging. A focal reducer or a telecompressor is basically an optical element that is used to reduce the focal length. So when your focal length is reduced, your lens speed is increasing, or f ratio increases, which improves the optical transfer function. Then when a field flattener is basically a field corrector, which makes sure that the light equally distributes on your detector and it does not create any vignetting effect. And then you have shutters. Shutters are basically your doors to open and close your equipment. There can be a shutter for CCD, there can be a shutter for primary mirror, there can be shutters for secondary mirror. And your motor focuser is a focuser that you attach with primary mirror or secondary mirror, and you use motors to move the mirrors forward or backward to basically create focus or fine focus. Because you created your rough focus with the back focus, but you still have to create your fine focus using a rotofocuser or a motor focuser. And then in the end, you have to protect your equipment. And if you have a small equipment, you can use your carpenter skills to make a cabin like this. This is a triangular cabin. It opens three ways. Or if you have money, you can buy this complete shell commercially off the shelf and integrate it. Or you can just put two wheels here and have a retractable roof using servo motors and put it backwards. Or you can just buy a full-fledged dome. And a dome also has motors, and those motors are connected with your system. The system is connected with the computer. So as the telescope rotates, your dome rotates as well. Back in the day, they used to have manual dome, move it, or they would have to have a separate computer and separate motor system to move the dome. And they had to synchronize that system with your optical system. So there was a lot of work. And then for atmospheric control, you need to have a weather sensor, which basically tells you the weather. For example, if you are doing night observation and all of a sudden a thunderstorm comes in, your weather sensor will raise an alarm and it will just tell you. And even if you are doing observation from remote areas, you can actually have the entire setup operated remotely. And for that, you must have a weather sensor, because if the clouds come in or if the weather is changing, you can program that with your software and it will automatically raise an alarm. Then you have an all sky camera, which will basically keeps on taking pictures of the entire night sky. And for example, you see a meteor here, or you can see different events, or if there is an incident in the night sky, or maybe there is a light pollution source, then you can observe your data and see how it is, how you can minimize the light pollution. And then similarly, this is a seeing monitor, and seeing is basically astronomical seeing is how far you can differentiate between two stars if the two stars are really close together. So using the data from seeing monitor, you can basically have a statistical estimation of the quality of seeing, astronomical seeing, that your observatory setup is providing. And then this is a paper I wrote last year in which I introduced the observatory rating process. So basically your telescope design, axis encoders, slew rate, detector focus, and calibration. These are the scores, maximum scores, and you evaluate your system and assign them different scores. And this is the rate of the night sky. So you can see 7, 8, 9 have really poor metrics. And however good your equipment is, if it is in the inner city sky, it is going to perform at 1/10 of its capacity or even worse. Similarly, this rating process is introduced so that the amateur astronomers community can use their telescopes for space traffic management or space situational awareness. And this is not tested, it is just a proposal. And once maybe if 100 or 200 different small observatories put their setup through this evaluation and calculate their I index, then over a course of a period of 1 year or 2 years, we can see that there can be a threshold I index above which you get good quality data and below which you don't get good quality data. So it really depends on experimentation of this process. And here we have, I have a chart that I pulled from my paper, which tells you about the need for standardization, its need, process, and approach. So if you want to read my complete paper, it's called Streamlining GeoSSA Data Acquisition, Processing, and Contribution from an Amateur Astronomer's Perspective using less than 1 meter aperture telescopes. So I presented this paper last year in Paris, but everything in this presentation, the detailed literature for that should be present in this paper. And the next webinars should be about ground segment and the software segment. And basically this is the end of my presentation. And now we'll discuss and go over the questions and see how we can answer some of your questions. So, wow, a lot of questions. Can I have the people who have put in the questions just speak out loud for what the question is?
Yeah, sure. If you prefer that, then I would request the people who have put down their questions in the chat to unmute yourself and directly ask Mohan.
Imad, why don't you go ahead and ask your question first? I see that you have 3 questions. You can ask them now. Okay, so never mind. Your first question is, what are the key considerations for selecting the appropriate commercially off-the-shelf equipment for SSA observatory? And how do these choices impact the overall effectiveness of the system? Your biggest driving factor is the money you have. If you have $500,000, you can get a pretty reasonable observatory. If you only have $100,000, you will have smaller equipment, less quality equipment. But what I say is focus on 3 things. Focus on your mount, your telescope, and your detector, and improvise all the other things. So you use your local machine shop for your adapters, for your foundation, for building your observatory cabin, your retractable roof, your dome. Your domes are really expensive, so you don't have to buy them. But the most important factor is money. And then you make a decision matrix and you put different options for the different things you want to buy. And basically you have different permutations for different telescope, detector, and mount. And then you choose the one that optimizes your performance. And then you have, are there any specific strategies or techniques employed to mitigate the impact of atmospheric conditions on the performance of the optical sensors in the observatory? Okay, if it's raining, you can't do anything. If it is, you have full cloud cover, you can't do anything. However, if you have light pollution, you have a light pollution suppression filter. If you have just atmospheric attenuation, you can use different sets of filters to basically improve your data and maybe relocate your observatory to a darker night sky. But more than that, these are very realistic limitations. You can do more than that. Next question is, what measures are taken to ensure the observatory's optical sensors can effectively track and monitor objects in various orbits? Okay. My personal experience is that it is really, really difficult to detect and track low Earth orbit objects because they are moving very fast in the night sky. So for that, you need a really good system. And you also have irradiance limitation. Usually just after sunset and just before sunrise, the sun angle is enough for the sun to put light on your object, and then that light comes into your sensor. So for low orbit objects, it's primarily right after sunset and before sunrise that you can effectively detect them. And then if you have to track them, your slowing speed of your mount needs to match the orbital speed of the object. And even you need to have really fine accuracy of your system, because once it detects, then it has to, like, the telescope has to keep on looking at the object and constantly move and keep it at the center of the frame. So you need a bit of advanced equipment for that. But for medium Earth orbit and geostationary orbit, it's really easy, and it's most effective for geostationary, then for medium Earth, and then for low Earth orbit. So how do you handle the vast amount of data generated by the optical sensors in the observatory, and what steps are taken to ensure efficient processing and analysis of this data? Okay, so the data segment comes into the ground segment of this webinar series. So my thesis for my master's was primarily about how we are going to design the ground segment, what levels of backups we're going to have, and what cataloging framework and networking architecture we have to have in such a setup. So, but mostly you need to have a lot of storage space, and you need to have collaboration with other optical networks as well. So you mentioned your design of a geo-based satellite. What was the magnitude of the uncertainty introduced by using a non-inertial satellite to perform your orbit determination? Okay, that's a really good question, and equally difficult as well. But I think we didn't had a non-inertial system. Our system was inertial, and I don't really have a number for the uncertainty, because I have to go back and look into it. But for the most part, the satellites that are under geo function best when they are looking laterally towards the geo ring. Because what you do is you look laterally once the satellite is approaching, you look laterally once it is leaving your field of view, and then you can have one measurement once when it is looking right at you. So what you do is you have a small arc here, a small arc here, a small arc here, and using short and long arc orbit determination process, you you compute your orbit determination. But to be very honest, it was giving a lot of uncertainty in the beginning. And what happens is you need to have statistical data. You need to build up a repository of data about particular visiting space objects and carry on with the process over the course of a time period and increase the frequency of your measurements of different objects to basically get rid of the uncertainty. How do optical sensors contribute to the overall accuracy and precision of tracking and cataloging space objects? Okay, it's a subjective question, but for geostationary orbit, there's a company called ExoAnalytics. It's doing a really good job, but the level of complexity basically comes with your orbit determination, because one measurement from one sensor is useless. If you have a network of optical sensors spread across, and you task your sensors in a manner that one particular object of consideration is repeatedly observed in one orbit, and those repeated measurements are then triangulated and put into statistical orbit determination process, it is only at that point that you improve your covariance and have a pragmatic way of space traffic management. There are very few sensor networks that are doing that at the moment. Of course, there is the US Space Surveillance Network, there is European Space Agency's network, There is China's EBSCO network, not very effective, and the IZON network. But I believe that there should be a lot more. Okay, Trevor, as you mentioned, optical sensors can provide both brightness and orbit information. How well can a cost sensor resolve the change in brightness? Trevor, can you go ahead and tell me what is a BRDF model?
Hey, can you hear me?
Yep.
The I'm gonna forget the acronym, bidirectional reflectance. The acronym doesn't matter. It's a model of the light coming off the satellite,
Okay.
so that you can identify it.
Okay, so as far as my limited knowledge is concerned, what you do is your sensor is just a sensor. Its job is to sense. It is not, I don't think a sensor can do something technically to basically improve the brightness or get rid of the brightness. The brightness is coming from albedo, earth shine, the actual sunlight reflecting off the sensor, and then the technical specifications of your setup. So your aperture, your focal length, and all that. So once all of those things are constant, your brightness would change constantly because your satellite is constantly either yawing or rotating or tumbling. So what you do is you have non-resolved imagery in the form of a video for that object, and you plot a graph of how the brightness is changing. Then you use a software like Blender to have a 3D model, a CAD model of that satellite. You put it into Blender and you basically simulate it. And then you match that simulation with the brightness and assess the behavior of the object. So these are some of the techniques that you can use to how in basically playing with the brightness and how the brightness information can yield information about the characterization and behavior of the satellite. Can you say something about the lifetime of this equipment? How much maintenance is required? Okay, yeah, so usually if you have it really depends. It depends on the quality of your equipment. But if you spend, let's say, $250,000 and have a good 0.5 meter aperture optical tube assembly, a good fork mount, a good detector, it can easily last you 15, 20 years. But you have to do scheduled and unscheduled maintenance on your equipment. You have to regularly clean it. You have to take care of your mirrors, your lenses. You have to shield it properly. And then there are different techniques to clean the mirrors, clean the lenses, and maintain them. So 15, 20 years, it's easily you can use it. After 15, 20 years, I think it will still be usable, but the technology would have matured to such an advanced level that it may not be compatible with the software or with the advanced things that are there in the market at that particular point. So do you have experience of observatories that host telescopes for hobbies or commercial companies? I have, there's a very famous astronomer. He's from Netherlands and he teaches at University of Leiden. His name is Dr. Marco Langberg. And he basically conducted a lot of his data, collected a lot of his data through observatories that are remotely available. Now a lot of observatories you can access or request to use remotely, and even for after paying some amount of payment. I don't have the names right off the top of my head, but definitely there are observatories these days that you can access either through a research proposal or by paying the money. I mean, money is a solution for everything. So I believe I have covered all the questions, but if there are more questions, if anyone wants to pass a comment, um, say something, that would be great. I'm still a young professional, so my knowledge and my experience is still limited, but I have tried my best to bring you all this information, and I hope this has helped. If you don't have any questions, any feedback, what you would like to know more, comments, concerns, anything.
Well, thanks so much, Mahad. That was such an enlightening presentation. I really enjoyed it throughout, and I'm sure everyone did. If you could also share some means to contact you, maybe your email ID or any of your social handles, then people can reach out to you later on.
Yes, I'll write my email, so please feel free to email me. You can also connect with me on LinkedIn. That's my name. And you can also follow me on Insta, this is my Insta handle. And yeah, I should be there in Baku. So if you are coming to IAC or SGC, that would be phenomenal to meet you. Anyone else with any comment or question?
Well, probably not, but you all can surely reach out to Mahad through his email ID or other social channels if you have any questions in mind or if you want to connect. Mahad, once again, thank you so much for your time. It was a wonderful webinar, and we are absolutely hopeful of doing this again. And let's have many more webinars with you. I'm sure everyone will benefit out of it.
Thank you, Subhajit, for doing all the administrative work, and I really appreciate your cooperation in this regard and for giving me this opportunity. Really appreciate your help. Thank you.
Thank you so much, Mahad. It was a pleasure working with you. And thanks to everyone as well for joining us today. And hopefully in the near future, we will again have another very interesting webinar for you. So hope to see you all again there soon. Mahad, thank you so much. Have a great rest of the day and rest of the week as well. See you all again soon. Thank you so much for joining.
Thank you everyone for joining. Really appreciate your presence. Take care. Have a great day.